Okay, let's practice that shortcut skill of differentiation now, please. I will give you several functions, and what I'd like you to do, please, is to tell me what the gradient function would be for each of them. So here's your first one, y equals x to the power of 5. This doesn't have to be done in your notebooks, either on a piece of paper or on a whiteboard, please. Can you tell me what would be the gradient function for the following equation? Okay, so bring that power down, reduce the power by 1, and we get dy by dx equals 5x to the power of 4. Number 2. So same again, dy by dx would equal 7x to the power of 6. We've brought that power down, reduce the power by 1, make sure that you include the dy by dx as well. What we wouldn't want to see is just the 7x to the power of 6. It has to be defined as dy by dx if you're going to get all of the marks. Number 3. So a little bit different this one. So first of all, we've got a coefficient of 5 already there. So how do we deal with that? And also our function is written as f of x rather than y equals. So don't forget to use the right notation when you're writing down your gradient function. Okay, good. So f dashed x would be 15x squared. We're multiplying by the old power and then reducing that power by 1. Number 4. So same again, we had a coefficient of 10 already there. So our gradient function, which would be called dy by dx this time, dy by dx will equal 60x to the power of 5. Next one. So this is the first time we're seeing two terms within the equation. So deal with each of them in turn, and that will give you your gradient function. So dy by dx equals 4x cubed minus 2x. We could write it as 2x to the power of 1, but of course we don't need to. All right. And then this is probably the most interesting of all the ones that I'm going to show you in this section. There are a couple of special cases that we need to discuss, but have a go first and see what you can come up with, please. So what is the gradient function here? Okay, so the gradient function for this equation would actually be 25x to the power of 4 plus 6. So let's have a think about why that is the case. So first of all, because I gave you f of x, then the gradient function is f dashed x. 5x to the 5 differentiates to 25x to the 4. That's just following the same skills, the same rules as I've just shown you. But what about the 6x? Well, 6x on its own differentiates to 6. Now let's think about why that is. Well, 6x to the power of 1 is how 6x can be written in a different way, just with the power of 1. And then if we use differentiation using those laws that we've just learned, when the 1 comes down to the front, 6 times 1 is 6. The power gets reduced by 1, so x to the power of 1 becomes x to the power of 0, and x to the power of 0 is 1. So together we get just a value of 6, a constant of 6 when we differentiate 6x. And that would be the same, of course, if we had 7x, it would differentiate to 7. If we had minus 2x, it would differentiate to minus 2. And the reason for that, if you think about the graph of y equals 6x on its own, the graph of y equals 6x is a straight line. And so it wouldn't matter where we choose our point on that straight line, the gradient would always be the same. So the gradient in this case of y equals 6x will always have a gradient of 6 wherever you choose your point on the line. And then finally, if we look at our final term, which is just the 4 on its own, we could write that as a power of x, and we would do that by writing it as 4x to the power of 0. And so when that power of 0 comes down to the front, it becomes a multiplier, and then the whole thing disappears. And the other way of thinking about why it disappears and becomes 0 is the line y equals 4 on its own is just a horizontal line through y equals 4. And any line that is horizontal will always have a gradient of 0. So that's why any constant on its own, when differentiated, becomes 0. and therefore doesn't need to be included in the gradient function. The final two are for when we have negative or fractional powers, and the rules still apply. You deal with them in exactly the same way as we've done the others. So have a quick go on your whiteboard. What would be the gradient function for f of x here, please? Okay, good. And again, use the right notation. We would get f dashed x equals, and then the power gets brought to the front. We reduce the power by 1 minus 2x to the minus 3. Just be a little bit careful here. We do see a lot of students writing the power as minus 1 rather than minus 3. So be careful. And then finally, our last function involves a fractional power. So what would happen here if we differentiate? Write it down on your whiteboards. Okay, good, and we would end up with f dashed x equals 3 over 2 x to the power of a half for the same reasons as all the others. We can write it as 3 over 2 root x, of course, based on the skills that we learnt last half term, but unless it asks you to, this would be a perfectly acceptable answer. Okay, good. So I think we need to write some notes on what we found out here. So in your notebooks, if you can put the big title differentiating, please, or as you can see here, differentiating x to the power of n, and let's write down those rules that we've just discovered. So first of all, very general, so it's always better to have a look at some examples like we did before I show you this, but here is a general example of what we've just learned. What we're going to do here is to multiply by the old power and reduce the old power by 1. So if y equals ax to the power of n, then dy by dx equals anx to the power of n minus 1. So that's the rule that we've been using for all of those examples you've just been doing. The next thing we can write down is what happens if you have two or more terms within the equation, and of course what happens is we deal with each of them in turn. So dy by dx would equal n lots of x to the power of n minus 1 and mx to the power of n minus 1. The third example talks about what happens if we have just x's, so y equals 6x, y equals minus 2x. We've talked about the fact that this would be a straight line and therefore would have a constant gradient, and that gradient function would be the constant a. And then finally, what happens if our original equation is a constant? Then if we were to draw that, it would represent a horizontal line, and therefore in every case the gradient function would be 0. Okay, so we wouldn't just be asked to differentiate an expression, we'd be asked to use it to find something, and I'm going to take you through a series of slides that show you exactly how differentiation can be used for different aspects of the course. So this is for your notebooks, please, and this is where we're going to be finding the gradient of a curve at a particular point. A bit like differentiation from first principles, but we're able here to use the shortcut method rather than the first principles method that we saw in the last presentation. Okay. So first of all, we read the question carefully. The question is asking us to find the gradient. All right. So if the question had have asked us find the coordinate of y when x is equal to 4, then of course we would be placing our x value into the original equation that's given here. That would give us our y value, and then we could write down the coordinate that we find. And often that will be needed to be found, but in this question that's not necessary. The question is asking us to find the gradient, and therefore in order for me to do that I need to have a gradient function. So the first job is to differentiate our equation. So before I can do that, I need to have the equation written in a form that I'm then able to differentiate. So 1 over x squared is not useful to me. The cube root of x is not useful to me. I would rather have those written in a form that I can use. And using your skills from last term, you should be able to tell me that 1 over x squared is the same as x to the power of minus 2, and the cube root of x is the same as x to the power of a third. And at that point, I'm now able to differentiate. So the same idea again, multiplying by the old power, reducing the power by 1. Be careful when you're taking away 1 from fractions and from negative numbers. We often see mistakes made with that. Now I could, if I needed to, I could tidy this expression up into something that looks a little bit nicer, but there's absolutely no need to do that. And the reason why there's absolutely no need to do that is because I have my x value. My x value is 4. So all I'm going to do is place that directly into the gradient function, and that will give me my gradient. So this is me now subbing in the value of 4. Looks a bit messy, but there's nothing to stop me from using my calculator to work this out. And when I do that, I get a value of 0.101. So that is the gradient of the curve when x is equal to 4. I know for a fact that this is not an exact answer. This is a rounded value from what was a horrible decimal on the calculator. So I have rounded it off to 3 significant figures for this particular question. Okay, so we've covered a lot there. We've differentiated different functions, and we've also then found gradients of curves at particular points, and we need to practice all of those skills. So on page 97 and page 98, there are 2 really good exercises that allow you to test that skill. It also allows you to test your skill in being able to manipulate algebraic expressions, which is something that we see come up a lot within this course. So have a go at these 2 exercises. Any problems, speak to your class teacher, and when you're ready, I will see you on the next slide. Good. Now a big topic within this differentiation section is the finding of an equation of a tangent, or it might be finding the equation of a normal, and I'm going to explain both of those to you in this section. So first of all, we need to decide what it means by finding the equation of a tangent of a curve at a particular point. This is exactly what we're being asked to do here. So I'm going to guide you through it, and I would suggest that you write notes on this as we go along, and then you'll be able to use it as an exemplar when it comes to the textbook exercise. Okay. So we already know from other topics that the tangent to a curve is a straight line that touches the curve at exactly one place. And that tangent line is going to look different depending on whereabouts on the curve we choose. So in this particular question, we're going to be choosing the point x equals 3. So here's the quadratic. You wouldn't have to draw this quadratic when it came to the question. This is just for demonstration purposes. So here is my quadratic. Here is the value, here is x equals 3. This is the point at which I am interested in. And here the red line shows the tangent line at that particular point. And it is this red line that I am being asked to find the equation of. So for any straight line, we can use the forms that we saw when we were dealing with straight lines a few lessons ago. So your answer can be written in the form y equals mx plus c, or it could be written in this form. But again, a word of warning that if you are going to use this second form, then when you get all of your values, you must make sure that you collect together the like terms before you give your final answer. So the 2 things that we need in order to find the equation of that red line is the gradient of that tangent. That's gonna be important, and I'm also going to need a point that it passes through. So we're gonna do them one at a time, and the first thing we're going to do is to find the gradient of the tangent, and I'm going to do that not by drawing it and finding the gradient of the line in that way. I am going to find the gradient of that tangent by differentiating. So if I differentiate the curve, I get dy by dx is 2x minus 4. It's crying out for an x value to be placed into there, so I'm going to use my x value of 3 and I will get a value for the gradient of that red line of 2. And it looks like that is right according to the diagram. My gradient of my red line is equal to 2. I also need, as I said earlier, I also need the point at which it passes through the curve. So I have my x value, but I don't have my y value. So I have to take my x value, place it into the original equation, and that will give me the coordinate that's shown on my diagram. And if I do that, I end up with a y value of -6. You can do the maths on that just to confirm that you agree. And so now I have everything I need. I have my x value, I have my y value, and I have the gradient of the tangent. And so I can place everything into this version of the straight line. And I'm just choosing this at random. I could have chosen y equals mx plus c. So I'm going to replace y1 with -6. I'm going to replace x with 3. And I'm going to replace m with 2. And if I now manipulate the algebra, multiply out the brackets, and then collect together the like terms, my final answer is y equals 2x minus 12. And a quick look at the diagram, although normally you wouldn't have the diagram to look at, but a quick look at the diagram tells me that that is a pretty good answer for this question. So as well as being asked about tangents, we might be asked about normals. And to demonstrate what a normal looks like, I've got my quadratic here. Here is my tangent line that we've found the equation of just a moment ago. But we would also sometimes be asked to find the equation of the normal. And the normal line looks like this. So tangents and normals are perpendicular to each other. So as I've written here, the gradient of the tangent would be the negative reciprocal of the gradient of the normal. Now I'm showing you this because I don't have an example here of finding the equation of a normal, but in essence there is only one thing that is going to change instead of what we did with the tangent question on the previous slide. The only thing that's going to change is that when we find the gradient of the tangent, the gradient of the normal will be the negative reciprocal of that value. So there's only going to be one extra line in, and that will be to tell the examiner what the gradient of the normal is, because the dy by dx value that we found in the previous slide is the gradient of the tangent. Other than that, the method that we use is exactly the same. The point that it passes through is exactly the same. You can see it here. You can see that the point that the tangent passes through is the same as the point that the normal passes through. So the only thing that will change with questions that ask you to find the equation of the normal will be the gradient, and it's the negative reciprocal of the gradient of the tangent. The other way of writing this, of course, is that the gradient of the tangent multiplied by the gradient of the normal would be equal to -1 every single time. Good. So there's a need to practice tangents and normals, and the textbook exercise on page 100 allows us to do that. So feel free to do as many of those questions as you like. Any problems, ask your class teacher, but do get a mixture of both tangents and normals just so that you know exactly the difference between the two. And when you're ready to move on, then I will see you on the next slide. Good. So let's dig a little deeper, and let's have a look at a few more words, a few more bits of terminology that you're going to come across quite often whilst we're doing differentiation. So this can be something for your notebooks, please, as well. So the gradient of a curve, as we know, varies as the x value changes. We've been talking about this from the very beginning. And here is a typical cubic looking curve. And I'd just like to concentrate on one section of this curve, and that is this section here. So in this section, wherever I choose my point, the gradient is going to be positive. and I can either deduce that by looking at these tangent lines all the way up to the very top, or if I had the curve, I could differentiate, put in the values of x, and I would see that the gradient is positive in this section here. Now, whenever a gradient is positive within a function, it means that the function is increasing at this point. So it makes sense. The curve looks as if it's increasing in this section here, right up until the vertex, if you like, the first turning point. And so we say that when the gradient is positive, the function is increasing. Similarly, in this section here, we have a decreasing function because the gradient is negative, all the way up to the turning point that is our minimum point. The gradient would be negative on the curve, and therefore we would say that the function is decreasing. And then when we have a situation where the function is neither increasing or decreasing, what we have then is our stationary point. So on this particular curve, we have two places where there are stationary points. And at these 2 points, we do not have an increasing function, we do not have a decreasing function, and therefore when the gradient is naught, we class that as a stationary point. Now, if we take the first of our stationary points on this curve, you will notice that just before the stationary point, the gradient was positive, and just after the stationary point, the gradient was negative. And if that is the case, then what we have is a maximum point. We can see that it's a maximum point based on the shape of the curve, but by finding these values of the gradient just before and after the stationary point, we can deduce whether we have a maximum or indeed a minimum. Because on our second stationary point, which I've now highlighted, you will see that a value of x just before the stationary point would be negative, and just after we would have a positive gradient. And so if we have negative before the stationary point and positive after the stationary point, then we have ourselves a stationary point that is a minimum. So that's a nice way of defining, without actually drawing the curve, it's a nice way of deciding whether our stationary point is a maximum or a minimum based on those rules. Now, there are lots of words that mean the same thing when it comes to stationary points. So we have stationary points, we have maximum points, we have minimum points, we sometimes call them turning points, we sometimes call them vertices, but in all cases dy by dx is equal to 0 at any stationary point. And we'll do an example of finding the stationary point on a curve. Now, the curve that I've picked out here is a quadratic, and we've already learnt, of course, a method of finding the stationary point on a quadratic, and that is to complete the square. The problem is, however, is that if I had a curve that isn't a quadratic, then completing the square doesn't work. So a better method of finding the stationary point would be to use differentiation, because we've now defined a stationary point as having a gradient of 0. So we can use differentiation to find the stationary point rather than using the completing of the square method. So because the stationary point is when dy by dx equals 0, I've stated that, I've given this a bit of a narrative for the examiner. I would suggest you always define what a stationary point means before moving on, which is what I've done. Then I've differentiated, so I've differentiated my equation to get my gradient function, so dy by dx equals 8x plus 2. And because I know that my stationary point is going to be when the gradient is equal to 0, I am not replacing x, but I am instead replacing dy by dx with 0. And if I rearrange this equation, I can now find my x value of my stationary point to be -1/4. which is good, but it's only half an answer. And the reason why it's only half an answer is because if I need the stationary point, I need an x value and I also need a y value. So the final part of this question is to substitute the x value into the original equation to find the y value of the stationary point. And if I do that, and again you can use your calculators if you need to, but we end up with a y value of minus 29/4. And that would be it. That's the end of the question. But just to demonstrate that using the curve, you can see visually what this quadratic looks like. And you can see that down here at the bottom is my vertex, my stationary point, my turning point, whatever you want to call it. In all cases, dy by dx is equal to 0. And I can see that the coordinate of that stationary point is indeed minus 1/4, minus 29/4. So lots to practice there: increasing functions, decreasing functions, stationary points, lots to cover. So there are actually 3 exercises that we can do to practice that skill. They're all shown here on this page. Have a go at lots of different types of question, please, and ask your teachers if you have any questions. And when you're ready, I will see you for the next part of the presentation on the next slide. The next thing that we're going to do is just revisit that idea of sketching curves, because we did a lot of work on this a few weeks ago, and we sketched curves based on 2 things really. One of them was the y-intercept and the other was the x-intercepts, and that's good, but there's more that we can do, and the new improved way of sketching curves can be to also find the turning points as well, the stationary points. And that's going to be handy when it comes to this example, and we'll see why as we develop the answer. So again, personally, I think that this would be a good example for your notebooks, but the reason why notebook isn't mentioned is because perhaps we've done this before in a previous presentation. So the question is asking us quite clearly to show all the intercepts, so that's the x-intercepts, the y-intercept, and also we're being asked to show where the maximum and minimum points are as well. Now, just to save a bit of time, what I'm doing here is I'm showing you that x minus 4 is a factor of this cubic. Now, normally you can either do that using a trial and error approach, or perhaps in the question they would guide you to the point where you would know that x minus 4 was a factor. But you can check that for yourself by taking x equals 4 and placing it into the function, and you will find that you get an answer of 0. So x minus 4 is a factor, and the resulting quadratic from that factor is x squared plus x plus 4. Now, one thing to notice about that resulting quadratic is that the discriminant is less than 0. So these are all words, these are all expressions, these are all phrases that we've covered in previous lessons. So because the discriminant of the quadratic factor is less than 0, that means that it can't be factorized or indeed solved. And therefore we can do no more with this function. So actually there is only one x-intercept, there is only one root, and that is the value of x equals 4, which I've now placed on the curve. So that makes it difficult. That makes it difficult for me to decide where the other part of the curve should be drawn, because I've only got one x-intercept. If I had the traditional 3 x-intercepts for a cubic, it would make my job a lot easier, but unfortunately I only have one. So what other bits of information can I find in order to help me to sketch this curve? Well, the first thing is that I can find the y-intercept. So I find the y-intercept by making x equal to 0, and it turns out that that gives us minus 16. So I've shown that point on my axes as well. And if I was asking you this question a couple of weeks ago, then that is pretty much all we could actually find. And then I'd be, I'd sort of be guessing whereabouts the curve should be drawn in order to get a fully correct answer. So instead, what I've now got in my armory is a method of finding the stationary points, and that's what's going to allow me to finish off this question and draw a pretty accurate curve of this cubic. So I am differentiating my function to find my gradient function. I'm then going to make the gradient function equal to 0 because that's what happens to find a stationary point, because the gradient would be equal to 0. And then I'm going to factorize my resulting quadratic. First of all, I've divided by 3, as you can see here. And now I would be taking x out as a common factor. It's one of the easier quadratics to factorize because there's no number on the end. So I'm taking x out as a common factor, and that would give me this factorized version here. And that then allows me to say that the stationary points are going to be when x is 0 and when x is 2. And if I put those values back into the original equation, I've now got the coordinates of my 2 turning points. One of them is in the same place as my y-intercept, and the other one is at 2 minus 20. And the final thing that I know about this cubic that is going to help is because it's a positive x cubed cubic, it's going to come up from the bottom left-hand corner. And now I've got everything I need to be able to give an accurate representation of that cubic. So here it comes up from the bottom left. The y-intercept ends up being the maximum point. It then goes down to the minimum point at 2 minus 20 and then up through 4, 0 to complete that cubic curve. The graph that has now been placed on top of the cubic is the gradient function. So I've plotted the gradient function for you to look at as well. So these are the values for the gradient at every single point along the original curve. And you can see that when the gradient curve is positive, in other words, when dy by dx is greater than 0, which is highlighted on the dy by dx graph, then because the gradient is positive, it means that on the original curve, as you're seeing at the bottom of the diagram, the gradient is positive at every point along the curve in that section. Similarly, if I look at this section here, which is where the dy by dx, the gradient function is less than 0, where the gradient is below the x-axis, where the gradient is negative, you can see that on the actual original graph, the gradient is negative between those two stationary points. And then finally, if we just identify a single point where the gradient graph is equal to 0, you can see that that corresponds to a stationary point on the original graph. So that's just to show you how the gradient function graph is linked in with the original function graph. Good, so we're nearly there. The only other thing to look at within this presentation is to look at what's called the second derivative. So this is if I take the gradient function dy by dx and I differentiate it a second time. If we do that, the notation for it is this, which you're seeing here. So this is if I took the original function and differentiated it twice, or if I took the gradient function dy by dx and differentiated it once. So this is called the second order derivative, and we would describe this as d2y over dx squared. If, however, we have a function given to us and we're using function notation, then the second derivative will be given as f dash dashed x. Now, second order derivatives are really useful, but they're only really useful for one thing, but that one thing they're very good at, and that is to allow you to decide whether a stationary point is a maximum or a minimum. We looked earlier at another method of doing that by considering the gradient either side of the stationary point, but this is probably a quicker and better way of deciding whether the stationary point that you have is a maximum or a minimum. So we've differentiated once, we've found where the stationary point is, we don't have the curve in front of us, and now we've got to make a decision about whether it is a maximum or a minimum. So what we would do is we would take our x value that we've found to be where the stationary point is, and we would place that value of x into the second derivative. And the rule is a bit unusual, it's perhaps not what we would expect, but if the if the second derivative value is positive, if it's greater than 0, then what we have is a minimum point. And if it turns out that the second derivative value is negative, well, that would imply that we have a maximum point. And the last exercise that I'm going to show you and ask you to do involves you finding second order derivatives and then making that decision about whether you have a maximum or a minimum stationary point. So here is that exercise. So we've got exercise 3.1 on page 101. We've got exercise 4.4 on page 107. Practice as many questions as you feel you need to in order to get a good understanding of what we've covered there, and then that completes that presentation on differentiation. It's been a bit of a mammoth one, but the skills that we've picked up within this presentation are going to serve you well for the rest of the 2 years on this course. So thanks for listening, and I will see you next time.